Okay, in this video, I'm going to go through A-level chemistry, AQA paper 3, and this is the June 2017 paper. I'm doing the second half of the paper here, starting off with the multiple choice, because I've already, in an earlier video, I've covered the first half of the paper. So 5, which compound has the highest boiling point? They're all similar molecular weights, just looking at them, but the answer is going to be A, because you've got an alcohol there, and alcohols can form hydrogen bonds. Okay, strongest kind of intermolecular force, obviously. So you need a hydrogen attached to an oxygen, which you've got there, and you've got lone pairs on the oxygen, so that can form hydrogen bonds with another alcohol molecule. All of these others, like the aldehyde, if you look, you've got a carbonyl group in there, but you've got lone pairs on the oxygen, but you don't have a hydrogen attached to an oxygen, so that's no good. You have no chance of forming hydrogen bonds. You're only going to get dipole-dipole interactions. The same with propanone there, that's just got a carbonyl group, and the ester, yeah, the same again. You've got oxygens, but you haven't got any hydrogens directly attached to oxygens to form hydrogen bonds. Okay, so that's the answer to that one. Okay, right. Order of melting points of these three period elements. Okay, so presumably starting off with the lowest melting point first. Right, they're all so we have to remember the actual answer here is going to be B, because of the kind of molecules they form. Argon is just atomic, of course. Chlorine is a Cl2. Phosphorus goes around as P4 molecules, and sulfur goes around as S8. So as the molecules get bigger there, you've got more electrons, higher van der Waals forces, higher melting point. So B would be the answer there. Okay, which statement is not correct? Transition metals form color dyes and complexes, correct. Variable oxidation states, correct. A ligand accepts a pair of electrons. Well, it doesn't accept. The ligand donates the pair of electrons, doesn't it? So like in water, the lone pair forms a dated bond to the transition metal line. So that one's the answer, because it's wrong. Okay, and D, of course, that's correct as well, isn't it? Right. Cracking, products of cracking of alkanes. So thermal, you have high temperature, but you don't get many alkanes, you get alkenes, don't you? So, and it's slight pressure. Actually, you probably want, right, this one is a possibility. Catalytic, slight pressure, you don't have high temperature, so that's wrong. Catalytic, high pressure, high temperature, no, that's wrong. This is the one. Okay, slight pressure, high temperature, and you get alkenes. Right, trichlorophenol is a weak monoprotic acid, and it gives you the Ka there. The concentration of hydrogen ions. So remember, when you've got a weak acid, H plus, all right, let's, so we have Ka is equal to H plus the conjugate base and the acid. Well, these two are equal, yeah. These two are equal in a weak acid, but you haven't added anything else to it, because all the hydrogen ions come from dissociated. So that simplifies as H plus squared on the top there. So H plus squared is equal to Ka times HA. So that is 2.51 times 10 to the minus 8 multiplied by the concentration is 2 times 10 to the minus 3. Right, that is going to give us 5.02 times 10 to the 9, square root it to get the hydrogen ion concentration. Minus 9, sorry. 7.08 times 10 to the minus 5. Hang on a minute. Sorry, that should be an 8 there. So this is wrong, sorry. That's 5.02 times 10 to the minus 11. And take the square root of that. 7.08 times 10 to the 6 is this one here. Okay, so that's a fairly straightforward finding the pH, well, not really the pH, it's the hydrogen ion concentration of a weak acid. The pH of 0.46 mole potassium meter cube potassium hydroxide. So we can, OH minus concentration is going to be the same, that's going to be 0.46. H plus, we're going to rearrange our Kw. H plus is equal to Kw over OH minus concentration. So that's equal to 1 times 10 to the minus 14 over 0.46. That gives us 2.17 times 10 to the minus 14. And we take the pH of that, the minus log of that. 13.66 is the answer. Minus log of that is 13.66. Right. Okay, what is the mass in milligrams of carbon formed when you've got that many moles of propene? Okay, so that many moles of undergoes incomplete. That's going to 1 mole of propene is going to give us 3 moles of carbon. So the moles of carbon is going to be 3 times 3, okay, which is equal to 9 times 10 to the minus 3. And so the mass of the carbon, multiply the moles by the atomic mass of 12. It's going to be that multiplied by 12, which is equal to 0.108 grams, but we want the answer in milligrams. Okay, so we have got to times it by 1,000, so it's 108, which is 1.08 times 10 to the 2. A sort of funny way of writing 108 there. Okay. Which compound gives this infrared spectrum? Okay, now look at this peak here. It could be a carbonyl or it could be an alkene. They're in a very similar range. But we can tell here because there isn't an alkene. There's no, so the only one that's got a carbonyl in there is butanol. Well, butanoic acid has as well, of course. But if you had, if it was butanoic acid, you would then see this broad, the broad peak for the acids. You'd see a big peak over here, and you're not getting that. So that is definitely C is the one there. Okay, which pair of compounds doesn't form a racemic mixture when the compounds react? Right, so we've got butene here, right? So what you're going to get is you're going to get electrophilic addition. You're going to get 2-chlorobutane, and that does have an asymmetric carbon atom. Butanol, yeah, when Cn minus reacts with that, that's going to go there. Nucleophilic addition. So you're going to have 4 different groups. You can have the cyanide, hydrogen, the R group, and that will turn into an alcohol. So that one does. HCl and let's do this one. HCl and but1ene. Well, you're going to get but2. You're going to get 2-chlorobutane again with that when you react that. You'll also get some 1-chlorobutane, but you'll get some 2-chlorobutane. The chlorine can either stick onto that carbon or that one. If it sticks onto number 2, then yeah, it's asymmetric. So it must be this one is the last one. And yes, look, this isn't. We'll just show why. But you won't get, you will not get a racemic mixture because there's no optical isomer possible there, because you've got CH3. Oops, sorry. You've got, in this compound, it's propanone, isn't it? Okay, so you've got CH3. When the cyanide comes along, it will stick on there, and that turns into an alcohol. It's not. This is not an asymmetric carbon because you've got two methyl groups. So D is the right answer there. 14 of a reaction sequence. Okay, but we just got to look out for the one which occurs by nucleophilic substitution. Well, this first step is free radical. That's not it. Free radical, and you need UV light for that. Here, though, step B, OH minus. Right, that's a nucleophile, and that you've got a delta positive on the carbon there, which is attached to the chlorine. So that is nucleophilic substitution. That one. Step C is dehydration. And step D is electrophilic addition. So the answer is B. Okay, cisplatin, the anticancer drug. Which structure represents a stereoisomer of it? Right, so some of these have got, this is wrong because these have got NH2 groups. The ligand isn't NH2, it's NH3. So that rule those out. This one is cisplatin. The chlorines are on the same size. This one is transplatin. So B is the answer. 16, Maxwell Boltzmann distribution. Which letter represents the most probable energy? Well, let's label the axes first. So you've got number of particles on this axis and energy on this axis. So it's either got to be C or D. At the higher temperature, well, it's going to be D, isn't it? Because the average energy is that's got a higher energy. So D is the answer. 17, vanadium 5 oxide here can be used in the contact process. Now the contact process is making SO3 from SO2. So we can rule out B because that's the other way around. So that's wrong, definitely. Okay, let's look at where's the vanadium oxidized? Well, oxidation state of the vanadium there is +5. Here it's +4. The vanadium's getting reduced there. It's not that. Here, this is going from +4 to +5, so that's possible, and this one's going from +5 to +4, so it's not that, so it's definitely C. Right, so this shows a section of a polymer chain formed from random polymerization of two different monomers. It's going to be addition. It's going to be addition polymer, quite obviously. Right, now what we could have is, let's just put, if we have, that could be one of the monomers, put a double bond in there. And the other monomer would be this next to it. Okay, that's a possibility. Another alternative, if you could just shift it along one, and then you could have that as one of the monomers, couldn't you? And the other monomer would be that. Well, let's look at the green option first. Right, have we got that anywhere? Well, let's look at this. It's quite easy to spot that one with just the one fluorine. Okay, so yeah, we've got that. Hang on a minute. That one there is that, and is this the other thing? See, yeah. No, that one is not that other one, so that's not it. This is the one. Okay, so that is the one there, and that is this one. Okay, so A is the right answer. It's quite fiddly looking at that. There's fluorines everywhere. It'll take quite a long time, but A is the right answer there. Right, an equation for zinc and hydrochloric acid. Minimum mass of zinc needed to react with that much hydrochloric acid. Well, we need to know the equation. Oh, we got it there. So look, it's we need 2 moles of hydrochloric for every 1 mole of zinc. So moles of hydrochloric, moles HCl, conc times volume is 1.68 times by 0.05 in dm cubed. That gives us that's equal to 0.084. So the moles of zinc we've got divided by 2 moles Zn is equal to 0.042. Okay, and so the mass of zinc multiplied by the atomic mass of zinc, which they tell us is 65.4. That gives us 2.75 grams. That's the answer there. Okay. Right. Right, we've got this equilibrium mixture, carbon monoxide and chlorine, giving the CoCl2. Okay, the temperature is decreased, and this is an exothermic reaction. So if we decrease the temperature, the equilibrium position is going to move to the right. Yeah, so the equilibrium moves to the right. So if we think that means Kp or Kc will get bigger because you've got more products and less reactants. Now it says which is greater? Well, the value of the equilibrium constant Kp, that's the answer, okay, isn't it? Because that's going to get bigger. Let's see, double check, make sure the other ones are not possible. The mole fraction of carbon monoxide won't get bigger. You'll get less carbon monoxide because that's a product and it's going to go forwards. Partial pressure of chlorine, again, that will drop because the reaction is going to go forwards. It's not that one. The total pressure of the mixture, now the total pressure is going to go down for 2 reasons. One, the equilibrium moves to the right, and you've got fewer gas moles on the right. And also, whenever you drop the temperature, that's also going to make the pressure drop as well if you don't do anything with the volume. Okay, so D is the right answer. Right, in concentrated alkali, propanone reacts with hydroxide ions to form an equilibrium mixture as shown there. Okay, so which curly arrow doesn't write? So what's going to happen here is we can see we've lost a hydrogen, haven't we? That's gone, and we formed a double bond there. So the OH minus is going to act as a base probably, okay? That's going to act as a base and remove that hydrogen. And we're familiar with these. That pair of electrons is going to go and form the pi bond like that. And then that means the carbonyl carbon's forming too many bonds. That's going to break, and that's going to form an O minus there. Okay, so which curly arrow doesn't appear? This one does, that one doesn't. That does, picking up the proton, the OH minus picking up the proton, and there the pi bond and the carbon are breaking. So B is the correct answer. That's the one that doesn't. Okay. Okay, pH curve produced by adding a strong alkali to a weak acid. Okay, they've kind of exaggerated this line. It looks very horizontal in this section. It wouldn't really be horizontal, it would be sloping upwards a little bit. At which point represents where it's acting as a buffer. Well, buffers pHs don't change much when you add acid or alkali, and so it's going to be that. You're adding alkali and the pH will only increase slightly, not by a lot. So B is the answer there. Okay, and also you're going to have a mixture, so B is the answer. Also for a buffer you need a mixture of a weak acid and its conjugate base, A minus. Okay, so you might think, oh, D, there's not much happening to the pH there, but at D you've gone way past the end point and you wouldn't have any HA, it would all be A minus. It would all have been neutralized by the NaOH. B is the answer there. Right, 2, 3. Which alcohol could not be produced by the reduction of an aldehyde or ketone? So they're kind of asking this question in the opposite way they normally do. What kind of an alcohol, basically saying what kind of alcohol can't you oxidize, okay? And you can't oxidize a tertiary alcohol. So you can't make a tertiary alcohol by reducing an aldehyde or a ketone. Right, so we're looking for a tertiary alcohol. 2,2-dimethylpropan-1-ol. It sounds like it might be, but it's not. So you've got 2,2, you've got your methyls there, and you've got OH on that end one. So that is actually a primary alcohol, isn't it? So that's, you can oxidize that. 2-methyl-butanol. That sounds hopeful because we've got the ol on carbon number 2, and we've got a CH3 on carbon number 2. So this carbon is a tertiary carbon. It's attached to 3 others. That's it. 3-methyl-butanol, that's a secondary alcohol, and pentan 3-ol, that's a secondary alcohol as well. So B is the right answer. Which compound does not show stereoisomerism? So we've got to think EZ isomerism or optical isomerism. So 1,2-dichloropropene. Let's draw that. 1,2-dichloro. Okay. Chlorine there, chlorine there. You can see that that can show EZ isomerism. 1,2-dichloropropane. Right, that's a bit sneaky. That can show optical isomerism because this carbon here has got 4 different groups. It's got HCl, a methyl, and then it's got this CH2Cl group. So that one can. So that this one can. This one can. 1,3-dichloropropene. Let's draw that here. That one can as well, I think. Right, yeah, because we've got EZ isomerism. You've got 2 different groups on this carbon, a hydrogen and a chlorine. And you've got 2 different groups on this carbon, a hydrogen and this CH2Cl. Right, so it's got to be this one. Let's just double check it. 1,3-dichloropropane. Right, now that, unlike the 1,2-dichloro, this one doesn't show optical isomerism because the middle carbon there has got 2 hydrogens attached to it. Okay, and it's also got 2 of those groups there the same as well, aren't they? So that's not an optically, and obviously these carbons have got 2 hydrogens, so they're not. So D is the answer. What compound can form a polymer without needing another reagent? Okay, so this one can't, because you've got an alcohol can't react with another alcohol. You need a carboxylic acid to form a polyester or something. This one's got 2 carboxylic acids on each end. Same problem there. They don't react with each other. They react with alcohols. This one can, because you've got an acyl chloride and an OH. So you can form, those molecules can go head to tail and form esters. And this one has got a carboxylic acid and a chloroalkane. Well, that can't react with a carboxylic acid. So C is the answer. Yeah, they're going to form. So they're going to polymerize by, you're going to lose HCl there, and you're going to form an ester linkage. Okay, like that. Right. A solution of lead chloride contains 108 grams of lead in 100 centimeters cubed. The lead is fully dissociated into ions. What's the concentration of chloride ions? Okay, so we've got 108. How many moles of lead chloride have we got? Moles PbCl2, mass over mR. We've got 108 over 278.2. That gives us 0.388 moles of lead chloride. Right, so the concentration in moles per decimeter cubed, moles over vol. The volume we have is 100 centimeters, so that's 0.388 over 0.1, which is equal to 3.88 moles per decimeter cubed. Okay, right, so then we have to, 1 minute. sorry, that's 3, that's times 10 to the minus 3. Okay, 3.88 times 10 to the minus 3, sorry about that. Let's change that. 3.88 times 10 to the minus 3. So that gives us a concentration equal to 3.88 times 10 to the minus 2 moles per decimeter cubed. And then we have the concentration of chloride. So 1 mole of lead chloride contains 2 moles of chloride ions in solution. So we've got to multiply that by 2. Which gives us a concentration of 0.0776 moles per decimeter cubed. Right, and that is that, isn't it? Times 10 to the minus 2. Okay, that's equal to 0.0776. It's that one. Okay. Right. Now we've got the rate equation for acid catalyzed reaction between iodine and propanone is that. Okay, so it's first order with respect to both. The rate of reaction was measured for a mixture of iodine, propanone, and sulfuric at pH 0.7. Okay. In a second mixture, the concentration of the sulfuric acid was different. They keep the iodine and the propanone the same. Okay, the new rate of reaction was a quarter of the original rate. Now it's first order, so therefore the H plus ion concentration is equal to original H plus ion concentration divided by 4. Let's work out what the original H plus ion concentration was. Right, that is, okay, so it's pH 0.7. So hydrogen ion concentration is equal to 10 to the power of minus pH, which is equal to 10 to the power of minus 0.7. And that is 0.199, nearly 0.2. Okay, so we've got to divide that by 4 because it's the new hydrogen ion concentration is the original divided by 4. That's 0.049 is the new hydrogen ion concentration. Now we need to find out the pH by taking the log of that. Minus log of 0.049 is 1.30. It's this one. Okay. Right. 28. Right, we've got a sample of carbon dioxide and some argon. Okay, what's the mole fraction of carbon dioxide in the mixture? So we need to work out how many moles of carbon dioxide we've got. We've got a volume, we've got pressure, so we're going to have to use the ideal gas equation. So PV nRT, that means N, the number of moles of carbon dioxide, is going to be PV over RT, which is 100 now times 10 to the 3, because we've got to have pressure in pascals, not kilopascals. The volume we have got to convert into meters cubed, so divide by a million, so that's times 385 times 10 to the minus 6. Okay, R 8.31, and the temperature is 25 degrees C. We need that in Kelvin. At 273, that's 298 Kelvin. So let's work out the number of moles, and that gives us that gives us 0.0155 moles of CO2. Right, now we've got to work out the mole fraction of carbon dioxide. So the mole fraction, let's usually use that lambda symbol, CO2, moles of CO2 over total moles. So the moles of CO2 is 0.0155 over 0.0155 plus 2.89 times 10 to the minus 2, that's 0.0289. So let's do that. .35. Okay, that's the answer. So ideal gas equation really, and of course plenty of possibility for making mistakes with the units. Yeah. Okay, how many peaks does this compound contain its 13C spectrum? Right, there's no symmetry in that compound at all, because that sulfur sort of messes up the symmetry. And so every carbon is different, so it's going to give its own peak. So we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. So D is the right answer. A student provided 5 centimeters cubed of 1 molar ammonia and was asked to prepare an ammonium solution with a concentration of 0.05 moles per decimeter cubed. What volume of water should the student add? So, well, the way I like to do these is, right, what are we diluting it by a factor of? We're going from 1 mole per decimeter cubed, and we want to dilute it down to 0.05. So 1 divided 0.05, 20, I think, is it? 20, yeah. So it's 20 times, it's a 20-fold dilution. So we've got 5 centimeters cubed. Okay. So we want to have a final volume 20 times that, which is equal to 100. 5 times, okay. 5 times 20. That's the final volume. So we don't need to add that much water though, because we've already got 5 there. So we only need to add 100 minus 5, 95. So that's the answer. A solution absorbs light with wavelengths corresponding to red, yellow, and green. Okay, so we've got Richard of York gave battle in vain. Now, what's it absorbing? It's absorbing red, yellow, and green. Right, so it's going to be probably look bluish color. Right, dichromate, that's orange, so it's not that. Fe2 plus is pale green, it's not that. That is orangey brown, so, and that's blue, so it's got to be copper. Okay. 32. A reaction is exothermic and a negative entropy. Which statement is correct? Right, so let's do this. Delta G is equal to delta H minus T delta S. Now, delta H, it tells us, is right, it's exothermic, so that is negative. And that tends to make delta G negative. But this is, because entropy is negative, this whole thing is positive. All right. So when T is big, that means the value of T delta S is going to be big, and it might be positive, big and positive, and it might be positive enough to cancel out the negative of that. So, right, so delta G will be negative at low temperatures. So the reaction is possible at low temperatures, but when the temperature gets really high, it might become impossible. So the reaction is not always feasible. No, that's wrong. The reaction is feasible above a certain temperature. No, when the temperature gets too high, it's going to stop. It's low temperature is not a problem. The reaction is feasible below a certain temperature. That's right. Okay. That is the answer there. The other way of doing that is, it's a bit, you wouldn't want to spend this long on a multiple choice question, but it's quite useful to remember that if you plot a graph, right, so you've got y mx plus c, plot delta G on the y-axis plot absolute temperature on the x, that means our intercept is delta H, and the gradient is equal to minus delta S. So for this sort of reaction, right, I'm going to draw a little graph. We've got delta G, and we've got absolute temperature. Now, the gradient is minus delta S, so we have got a negative, so our gradient is going to be positive, the line's going to go that way. The intercept is negative, so the line is, so that delta, the intercept is delta H, that's negative, so it's going to be like that. So you can see this reaction is possible at those temperatures, but when it gets to that temperature, delta G becomes positive, and so it's not possible at high temperatures. So that's another way of doing it. Okay. Oops. Right. Okay. Phenylethanone can be prepared by the reaction between ethanol, chloride, and benzene. Okay. Right. We're going to need aluminum chloride catalyst there. No, that's relevant. No, I don't think it is. In a preparation with an excess of benzene, okay, the mass of ethanol chloride used was this much. Okay. And the percentage yield was 62. What is the mass in grams of phenylethanone? Well, we need to work out the MR of phenylethanone. Right, the benzene ring, the C6H5 bit, that is 77. And then we've got plus 12 for the, so 77 plus 12 for the carbon, plus 16 for the oxygen, plus 15 for, that's 120. Okay, so let's now see 1 mole of ethanol chloride should give us 1 mole of product. Okay, how many moles of ethanol chloride have we got? Let's do that. Moles of the ethanol chloride equal to the mass, 5.7 times 10 to the minus 2 kilograms, so times 10 to the 3, divided by the MR, which is 78.5. Let's do that. That gives us 0.726 moles of that. So we get a 100% yield. We get 0.726 moles of the phenylethanone product. So the mass of the product is equal to the moles, 0.726, multiplied by the MR, which is 120. Which gives us 87.1 grams. But it says the yield was 62%, so we're going to do 87.1 multiplied by 62 over 100. That is going to give us 54 grams. So that is our answer. Okay, 34. I think this is the last question on the paper. Right, 130 centimeters cubed of oxygen and 40 centimeters cubed of nitrogen. Right, now we can just ignore that it's a different gas, because all gases can occupy the same volume and all that. So that is like having 170 centimeters cubed of gas. That's all we need to worry about. The pressure of the gas in the flask, well, we're going to use PV is equal to nRT. P is equal to nRT over the total volume of the gases mixed together. We don't have to treat them separately. So sorry, that's what we need to find out. Okay, this is they're both at 100 kilopascals. Okay. All right. It's an evacuated flask. Right. Okay, so we need to work out the number of moles of gas. Okay, let's do that then. So let's work out the number of moles of gas. And again, we don't have to treat them separately. We just treat them as one because it's all the same. So N, PV is nRT. N is equal to PV over RT. So we've got 100 times multiplied by 10 to the 3 because it's kilopascals. We need it in pascals. Multiplied by the volume, which was 170. Turn it to meters cubed, so times by 10 to the, divide by a million, divided by 8.31 and 298 Kelvin. Right, the total number of moles of gas then is going to be that's 6.86 times 10 to the minus 3 moles. Okay, now they put it into an evacuated flask. Okay, and the volume of that flask is 0.5. So we've got to use, again, the ideal gas equation. But this time we rearrange it to get P. So P is equal to nRT over V. The number of moles is 6.86 times 10 to the minus 3. 8.31 for the gas constant, and 298 again. And the volume of the container is 0.5 dm cubed, or 0.5 dm cubed. We need to convert that into meters cubed, so divide by, there's 1,000 dm cubed in a meter cubed. Right, so that's going to be divided by 0.5 multiplied by 10 to the minus 3. Let's do that. Uh, 34 kilopascals, 34,000 pascals. I get that to be, which is 34 kilopascals. So that is our answer. And that is the end of the paper.